Welcome to Designing Microservices with Serverless. My name is David Nasi. I'm a Senior Product Manager on AWS Serverless. And today I'm also going to be joined by Nick Kilnani, who's a Senior Director at NG Partners. And he's going to share later with us his team experience with serverless and building serverless microservices. So let's get started, but let's first do some baselining and kind of define what microservices actually, what this term actually means. So microservices is an architectural approach which advocates for creation of applications as a suite of independent services that interact with each other over the internet, typically using REST APIs. And these services can be and should be managed independently with minimal amount of central organization. Moreover, they can be delivered and deployed independently as well. They're scoped as part of, under a bounded context of different business capabilities. And a good microservice should have some characteristics which make it more resilient to failures, which makes your entire application more resilient to failures. But that doesn't really tell us about why you want to kind of embark on a journey of implementing a microservices architecture. So let's kind of spend some time talking about that. Essentially, there are two very high-level goals that you would like to pursue when you're moving away from having a monolithic architecture going into microservices. From the business perspective, you want to increase the pace of your innovation and the time to market to bring new features and new capabilities for your customers. From an organizational perspective, microservices encourage end-to-end ownership, which empowers your teams to own the service end-to-end, from development to operations to testing and everything that the software development lifecycle involves. And they are free to choose, the right tools to actually solve the problems that they're out to solve. Now, getting to kind of achieving these goals dictates that your microservices should adhere to some, high-level architectural pillars. And these are the pillars that we're going to discuss today from a serverless lens. And those pillars are resilience and how you make your entire application more resilient and how you make the individual microservices more resilient. Scalability is another one. And here you really want to make sure that your microservices are able to scale independently according to the resources and the traffic that they require instead of scaling the entire application. And the third one is continuous delivery, which enables you to deliver changes frequently but safely and reducing the cost of errors. So now kind of let's bring serverless into the picture and how all of this relates to serverless. So essentially with a serverless approach, you get a lot of the best practices that you want in your microservices out of the box. And the mental model with which you think about serverless applications very much aligns with the mental model that you want to have for microservices. And so the other best practices that you want to have are much easier to achieve and reason about. One point to make, though, is serverless definitely is not a silver bullet. So you still need to write your code efficiently and diligently, and properly log and monitor your applications, and test and so on. So all these still apply. So having kind of set the context for our conversation today, let's kind of start reviewing these pillars and how you can achieve them in a serverless microservice. And the first one we're going to talk about is resilience. When you implement your architecture as part of in a microservices fashion, they're interacting over the network. And network has some intrinsic qualities to it, which include that you can't rely on the network being reliable all the time, and you cannot rely on it having consistent latencies at all times. And so since these are the characteristics, you want to introduce additional robustness to your microservices and how they interact with each other. And these are architecting them for high availability, applying throttles for your microservices and the calls that they make, and employ retries and timeouts. And these are the essentials of implementing a good distributed architecture. So let's see how that kind of looks in a serverless world. When you build your applications and microservices on Lambda, you essentially get high availability out of the box. A lot of the things that, a lot of the best practices and things you need to implement in a traditional server full applications, like implementing your application to work across multiple availability zones and introducing additional redundancy, Lambda does all of that for you. And that applies both to Lambda, the service, and the functions that it runs for you. So it runs at default across in each AWS region across all the availability zones and has additional redundancy and resiliency. So that's great when you run in one region, but if you want to deploy your stack globally, there are some additional things that you might want to consider in order to have a truly global deployment. Now let me share with you how you can get to a global deployment with serverless application. So in this diagram, what you see is that we have a microservice which is composed of an API gateway HTTP endpoint, which is backed by a Lambda function. And what we have here is a microservice that is deployed, it's the same microservice deployed across two regions, US East 1 and US West 2. Now, here we're utilizing a feature that we just recently released in API Gateway, which allows you to set a custom domain, which will be integrated with both regional endpoints of HTTP, of API Gateway. And you can see here that we have DNS entries in our Route 53 setup, which point our custom domain, which is called Hello World API .replace with your own company name. We have that configured for both the US East 1 and the US West 2 regions. So what does that give us? Essentially now we can use routing policies within Route 53 that are available there. So you can apply latency-based routing. You can apply weight-based routing, and it will distribute the calls according to the routing that you define. So now we have truly globally deployed serverless microservice. But it's still not the full picture. We now want to introduce additional resiliency across AWS regions for a case where in one of the regions our microservice is experiencing disruption in availability. So how do we go about that? Well, Route 53 now allows us to set health checks across the different endpoints. So it will ping each microservice in each of the regions with a request and expect some sort of a response. And if the response is as expected, then it concludes that the service is healthy. And what you see here is a snippet from a CloudFormation template which sets that health check. And as we have that, now whenever one of the services doesn't behave as expected, the traffic will be routed to services that are deployed in other regions. So here we have implemented additional resiliency on top of what we get with just a regional deployment. And we have an active-active failover setup here. The next best practice is throttling. And let's first kind of talk about why do we even need throttling. In a microservices setup, we have microservices interacting with other microservices over the network. And the microservice that you own might be talking to microservices that are owned by completely other teams. And these services have different guarantees on the amount of traffic that they can serve. So as an owner of a microservice, you want to make sure that your service doesn't get overwhelmed by a sudden influx of requests. And the way to go about it is to implement throttling logic within the microservice. In this example that I'm showing, we have a front-end service which interacts with other 3 services, which all may have varying levels of traffic that they can support. So, in a traditional sense, when you implement your microservices, throttling is hard to instrument, both on the client logic, which makes the calls, and the downstream service that receives them. And let's go over some of the things that you need to implement in order to have throttling. So on the back end, you want to manage API keys to keep track of the users that are calling your APIs. Moreover, for each user, you want to have measurements of the steady rates that they make and kind of be able to put limitation on that, and also for burst rates. And if you really want to go granular about it, then you want to have all these capabilities for each method of your APIs. On the client side, you want to identify when the calls you make get throttled and adjust the behavior accordingly. So it's not an easy task, but when you build on top of serverless, this comes out of the box. And in this example, what you're seeing is how we can define a usage plan within API gateway, which does all of that for you as part of the configuration of your API. So you can set throttling for the overall request rate and set kind of burst buckets. And you can also set quotas for a period of time. And you can do so also very granularly across different API stages that you have. So that's good kind of for the downstream service, how it can protect itself. But then how do we monitor whether the calls that we make and what the rate of those calls that get throttled? And here you can use AWS X.RAY for generating a service map of that illustrates the entire your entire distributed application. And in this example, we have a very simple setup where we have a Lambda function calling to a DynamoDB table and Amazon recognition. So this is just an example of a service map that you can see. And it shows us very useful information on average latencies that calls take, and a whole bunch of other very, very good information. But in this example, what I want to draw your attention to is kind of the purple part of the calls that are made to recognition in DynamoDB, which are which represent throttle calls. So you can now understand that you have an issue with your DynamoDB table, which throttles the requests that are made to it. And you can then take action to remediate that. For example, one thing you can do is increase the capacity, the read capacity of your DynamoDB table to make sure calls are successful. The next topic we're going to talk about is how you set right timeouts and retries. And again, going back to my earlier point about network not being reliable, that requires you to implement both timeouts and retries. Without setting any timeouts, your application might just hang on a call on a response that will never arrive. If you set the timeouts for too short of a period of time, then you might discard or retry for responses that are arriving. So it's important to get that right. And there are some best practices to how you want to go about it. It's very hard to determine what is the optimal timeout that you want to have as you deploy your applications to production. It's something that is very hard to even test in a staging environment because the way network behaves in production is different. So the best practice here is really to log diligently, set default timeouts that look, sort of okay to you at start, and then log diligently when timeouts occur and adjust the behavior of your application accordingly. And for retries, you want to have retries that employ exponential backoff, so you do not overwhelm the services that you're making calls to. Now, when you employ timeouts and retries, duplicate requests might arrive to your microservice, and you want to be prepared for that too. So you want to have some sort of logic that deals with that, whether you make some, you apply some IDs to requests that you see, or any other logic that does that. And again, let's kind of apply everything that we discussed so far on timeouts and retries for serverless and how that looks in a serverless world. So with Lambda, you can actually set timeouts for your functions as part of the configuration of your function. And what that gives you is that now you don't have to have that as part of your code. So you can keep good hygiene inside your code where this kind of orchestration logic is moved to the configuration part. So your code maintains good readability, and you can focus on writing business logic which differentiates your application. When you use the asynchronous invocation mode for Lambda, and this is a mode which you can use with the APIs that Lambda provides, or also are associated with some of the kind of very popular event sources that Lambda supports, like S3 and SNS. So for the asynchronous invocation mode, you get retries out of the box. So if a message is not processed the first time, Lambda will keep retrying up to 3 times until it is successful. And moreover, you can then set dead letter queues for messages that weren't processed successfully and discard them there, and then set redrive policies for that dead letter queue to kind of process those events as well. Now, if you want to have a very elaborate orchestration of your different microservices and Lambda functions, you can use things like AWS step functions for that. And this is really kind of building on that capability of focusing on business logic and abstracting away state and orchestration to be something separate that is managed separately. In this particular example, what we see is a create account flow where a user tries to create an account. And if the user is successful, then you send a welcome email. And each of those rectangular nodes is actually a Lambda function, which only focuses on that very specific business logic. Now, if a welcome email, if a create account attempt is failed, then the step function state machine will invoke a catch clause, which then would run the suggest account name function, which would suggest the user a valid account name. So you can see we have a fairly elaborate orchestration here, which has nothing to do with our code and is managed separately. So we talked about kind of resiliency, reliability, and the second pillar we're going to discuss now is scalability. And as I mentioned previously, the characteristic that you want your application to have is that each microservice can scale independently. And again, discussing that in the serverless context, that again comes something that, that you get as an inbuilt capability. If you have your microservices implemented as Lambda functions, then each Lambda function will get its own scaling behavior that comes with built-in metrics and logging. And so, this is a very desirable state that as you get started, all of that comes built in. Now, Lambda will scale according to the number of events that it receives, and it will do so automatically on your behalf. So you never get to pay for idle because each Lambda invocation actually does some work. But that scaling behavior has some characteristics which I want to discuss with you because it might empower you to have some additional tools and a good mental model to improve the performance of your serverless microservices. So how does actually Lambda scale? Lambda functions essentially are architected on a container architecture. That is abstracted away from you, so you do not need to kind of manage any of that logic. But when a new event comes into your Lambda function, it will try to process it on one of the containers that it used to process previous events. And between invocations of a function, it will usually freeze those containers for some time and keep them in anticipation that more events will come in. If you're now creating a completely new function or a version of a function, or your application suddenly sees a big scale-up event where Lambda does not have sufficient number of warm containers to process those, it will create a new container. The former case that I described where it uses an existing container, we will refer to as a warm start. And the latter case, we call it a cold start. And there is some misconception when I talk to customers about those two. And the misconception is that customers kind of sometimes think that cold starts, is a big thing and has a profound impact. But actually, the vast majority of the invocations for an application that has any meaningful traffic will result in warm starts. So this is really an area where you want to put your focus on improving the performance of your applications. But there are some things to know about cold starts as well. So let's kind of look at the anatomy of a cold start. So what happens during a cold start? Lambda, the service, will download the code into the newly provisioned container. So it will download the code and start the container. And then it will initialize the runtime on which it runs and run all the global scope initialization included in your code. And only then it will invoke your handler code, and that's kind of where your business logic lies. So I'm telling you all this because now I want to share with you some best practices on optimizing the performance of your applications, both for cold starts and warm starts. So let's start with discussing cold starts and the things you can do there. The theme here really is that you want to minimize the complexity of the dependencies that you put as part of your deployment packages. One example for compiled languages such as Java and .NET would be to use the modularity of the AWS SDK, which allows you to import only the modules that you actually use in your function. So as an example, if you use only S3, if you only call to S3 from your function, then you only need those libraries to be imported into your deployment package. By doing so, you can shave off the size of your deployment package from 100 megabytes or so to single-digit numbers, and that would allow a faster download time for your code and also improve the initialization time. Building on that, you really want to reduce kind of the complexity of the initialization of your code. So instead of using heavyweight frameworks like Spring, again, in the Java world, for dependency injection, you might want to use something lightweight like Dagger instead. So that's another way to go about it. So we talked about how you can improve your cold start behavior. Let's now talk about warm start, because that's really the common case. And here, what you really want to make sure that within your handler code, the one that gets invoked across your invocations, you keep that code as lightweight as possible. And you don't perform any initialization that can be done prior. I shared with you kind of the container reuse strategy that Lambda has, and that gives you a lot of capability to keep kind of soft state within your code, within your global scope code. So things like global variables, or establishing connections to databases, or connections to an HTTP endpoint. All those should be done outside of your handler code. And then within the handler code, you only check that this initialization is still valid, or that connection is still valid, and only reestablish that if necessary. So we talked about scaling, and I hope now you have kind of more tools to apply some performance improvements to your serverless microservices. The third pillar that I'd like to talk about is continuous delivery. And this is really the core of microservices, because the entire purpose is to deliver changes more rapidly and increase the pace of innovation. And as you go about instrumenting a service, instrumenting a process, continuous delivery process for your microservice, you might want to consider 4 milestones against which you want to measure how good your process is. And let's quickly go over those milestones. First, your process should be the way you model your application or microservice, and the way that you think about your deployment process should be relatively easy to interpret. You also want to make sure that you are making frequent changes and do so in small batches. And those should have scoped impact to reduce risk of bad changes. And finally, to bring it all together, you want to automate the entire process. So how can we achieve all these 4 milestones in a serverless microservice? So let's talk about that and start with the first milestone. And there I want to talk to you about SAM, which is this cute squirrel, but it's also the serverless application model. And the serverless application model lets you have a template where you can define all the resources that are involved in building your microservice. This framework is supported by CloudFormation. So once you templatize your application and You can also then version it and share it with other teams. You can also use CloudFormation as the deployment engine for your serverless applications. So I talked a little bit at high level, but here's an example of how a SAM template can look like. This SAM template really defines, a basic microservice which involves an Lambda function connected to an API gateway endpoint and a DynamoDB table. And here you see that it's very digestible, easy to inspect, and it defines all the properties of that microservice, including where the code for it lives, what is the runtime that is used to run your Lambda function, what are the IAM policies that it requires, what is the integration type that it has with the event source, which is API gateway endpoint. And you also define your Dynamo table. And going back to my point, now this is something that you can really version, and as you implement additional changes and add additional resources to it, then that can be captured in one place. So now we can put a check on that milestone. Let's now look at how we can deliver changes frequently in small batches. And here we meet our old friend, the squirrel again, but here this is part of SAM Local, which is a local framework for you to test your applications and microservices on your workstation before you move them to the cloud. What this framework gives you is the ability to test your functions in an environment that has high fidelity to the execution environment of the Cloud Lambda, and do all the testing there before you're ready to perform a deployment to the cloud. And it comes with a lot of kind of capabilities that emulate the actual Cloud Lambda behavior, like timeouts and memory limits and runtimes, and also supports API gateway for the proxy integration type of API gateway. And so as you test your function, you can then access logs locally on your workstation and really iterate very rapidly that way. Great. So the third thing that I want to talk to you is now how can you have scoped, how you can make changes that have scoped impact. And here I'm really excited to share with you a feature that is coming soon to AWS Lambda, and by soon I mean later today, which allows you to define pre-assigned rates with which traffic will be routed to your versions of your function. So we already have a concept in Lambda which is called ALIASES. And ALIAS is really a mapping to a certain version of your function. So just as an example, you can have a prod alias which points to a certain version of your function. And then you have a staging alias which points to another version. But before, something that you had to do when you deployed and wanted to deploy a new version to production is that you had to go all in. You had to route all the traffic to the new version to which that alias points to. With this feature, you can now point to two versions of your function. And as you roll out new versions of functions, you can assign specific percentage of how much of the traffic will now be routed to it. And with this capability, you can employ some of the deployment best practices, such as blue-green deployments or canary deployments, and so on. So I talked a lot, but I now want to kind of show you how that actually looks like. So in this example, we have a function called myFunction, and an alias, and we have only one version of that function. And we have an alias which points to that version. It's called myAlias. Sorry. And now we iterate on our function and we add some additional capabilities to it and now want to promote that version. So what we do is we update the function code, and we publish that as a new version of our function. And so far, it's all kind of familiar Lambda. But that third API call that you see here is what this feature is all about. So now we say to our alias, point to version number 2, and make 5% of the traffic that you see be routed to that specific version. And now you can really monitor your Lambda function for any increased error rates. And as you gain more confidence with how that new version performs, route more and more traffic to it until your entire, all of the traffic is routed to the newer version. Great. So now let's kind of see how that all comes together in a process, in how you can automate your deployments fully. And here I want to talk to you about using AWS Code Pipeline to build robust pipelines for deploying your serverless microservices. So we already talked about how with some templates you can now kind of version them, and by putting them in a code repository along with the function code and then connecting them to your delivery pipeline, what will happen in that situation is that with each commit that you make to your code, it will trigger an automated run of the pipeline and deploy your code to the different environments. And you can have multiple environments, such as a beta environment or a staging environment, production environment. And a typical flow of that would be that your code and the SEM template will be built and packaged, and you can have multiple options there. And you can connect your Jenkins to work as part of your pipeline, or you can use a fully managed service such as AWS Code Build to compile, build, and unit test your code, and then package it. And then across the different environments, you have integration with CloudFormation that can perform the actual deployment. So here, what you can see, an illustration of an environment which we call beta, which creates a CloudFormation change set and then deploys that set. And the last step is that we're running some tests against the newly changed code. And you can gradually onboard this until you achieve full automation. And what one capability of code pipeline that you have, if you don't feel that you're ready to go in a full automated way, is manual approvals that let you pause the deployment before it hits production and do some additional testing. Great, so now we have a good and robust continuous delivery process for delivering our serverless microservices. So we talked about the 3 architectural pillars with which you want to think about your serverless microservices. And let's kind of now bring it all together and do a quick recap of what we discussed today. First, we talked about resilience and some of the built-in capabilities that Lambda and API Gateway come with. And also how these capabilities allow you to keep your code free of any orchestration logic and have good hygiene for your code. And finally, we talked about how you can now have global deployments with cross-region failover scenarios. We then covered scalability and discussed how Lambda actually scales, and then discussed some best practices around how what are the things that you can do to improve the performance that you're getting from your serverless microservices. And finally, we talked about continuous delivery and how you can have a process that is easy to model and reason about, and how you can deliver changes across, starting from local development, spanning deployments to the different stages until production, and also how you can do that safely until you reach a fully automated process. So I hope now you have kind of more tools and skills to go back, and as you embark on your serverless journey, kind of apply some of these things to make your applications perform better and be more resilient. And that brings me to kind of what Nick is going to share with us. So I now want to invite Nick to share National Geographic's story with serverless and their experience with it. Nick?
Thanks, David. So I'm Nick, and I'm the Director of Software Platforms at National Geographic. And I'll level set a little bit of National Geographic. So National Geographic's main purpose, the main mission, is to really further people's understanding and knowledge about the world. And it's really trying to make you feel like an explorer every day in your living room. And a lot of people, when they think about National Geographic, they usually think about the TV channel and the magazine, but there's a lot more to it. So for example, there are products for travel, where you can take an expedition with an explorer. There are products for kids. We publish books. We have live events. And all of this is designed to create a 360 experience for you. And also over the years, National Geographic has really created a pretty large, strong reach. So we have around 6.4 billion content interactions across our digital properties. We reach around close to 500 million households on the TV side. We have close to 400 million followers on social. We're one of the largest brands on social on Instagram. And we're in 172 countries, 43 languages. And the real goal here, all of this is centered around creating entertainment with a purpose. And part of that is the National Geographic is the only media company that returns 27% of our proceeds back to the nonprofit National Geographic Society to further invest in science, exploration, conservation, and education. So as you can imagine, over the last 130 years, there's a lot of technology that's been built up. And we're really in a phase where we're going back and taking a look at all of our technology and trying to modernize our technology stacks as we expand more internationally now. So the interesting part is that we actually have a lot of technology sitting in data centers in the US. And we're starting to migrate everything to the cloud. And we're really starting this journey right now. And what we're trying to focus on right now is incubating new ideas and innovation. And that's what really brings me to the product that we launched recently called NatGeo One. And this is a mobile app that we launched in Australia. And it's in partnership with a telecom called Optus, and it's only available to subscribers of that telecom. And the goal was to try to create an application that really gives the user personalized content experience that really works well with the TV channel and the kind of content coming out there as well. And there are a couple of milestones that we hit with this application. So it is the first app that we've launched that actually has, a mobile app that we launched that has content from a variety of sources. So we have the magazine content, we have TV shows, we have live video, and social content all coming in one app. Another part is the first time we really have a lot of content for 130 years coming into one application as well. And then it's the first app that we actually built in serverless. So it's really a learning experience that we went through as part of going from something where we use EC2s and traditional technologies on Amazon, and then try to apply serverless technology along the way. So what's the application architecture look like? So this is kind of what we've landed up with, and it's kind of broken up in a couple of different phases. So the first phase is really where we're aggregating content. And we have a couple of different CMSs spread across the world. So for this application, most of the content is coming from the US and a content management system in Australia. And that's where we get personal content, localized content for the Australian market. And we have some upstream systems that aggregate this content and normalize it. But then we also have different systems for video. We have one for the US, there's a different one in Australia, live video comes from a different place, and that needs to kind of get aggregated over together as well and normalized. So we have a Node.js application that runs on EC2, and this really doesn't fit the serverless model, and this is something that I'm going to come back and take a look at. But it's really trying to aggregate the content, normalize it, and then prepare it for delivery. So we have a couple of layers of aggregation. So as I mentioned before, we do aggregation upstream, but that's purpose is to really normalize the data model. It's not necessarily suitable for delivery at the last mile. So what this Node.js app does is really kind of prepares the data It formats the data for what's appropriate for cloud search indexes and so on, and keeps it ready for a mobile app to use. And we also store files that we get, like image files and so on, into S3. And that brings us to the asynchronous processing, where we have events on Lambda functions. So when we get a file over, like an image file, we have Lambda functions that then resize the image, crop it, and so on. We also have other Lambda functions that kind of work with the recognition service. We have Lambda functions that keep information that's local to Australia up to date. So for example, show times, they need to be kept up to date for that market. What we have in the US may not apply there. And we also have Lambda functions that really work on personalization of content as well. And the last part is the delivery side, which is mostly powered through API gateway and Lambda functions. And we have our APIs really broken up into three. There's content, user, and administration. And the content API is really working with the data that's in Cloud Search. So we have feeds in Cloud Search, and that's the primary source of most of the content that goes into the application, and what the user sees in different sections as they navigate around. The user API is really associated with managing user state, session, what the user is doing in the application. It's kind of a read-write API, and it's really pushing data mostly back into DynamoDB. And the administration API is not really a content management API. It's more about positioning and administrating what a user can see. So for example, if you have some articles that someone deems is not appropriate for the Australian market, we can go turn it off. If you find that tagging is a little bit different in the US and we want to kind of reposition the content in the actual app, we can go in and say, okay, show this in a different section and change its position in the feed. So that's what that API does. And while each one of these do work independently from each other, if the user API is down, you may go in and get content, but you won't get personalized content, right? So it really doesn't work well. So that's where kind of things come together, is while you can build things to be separate, you really need them to work together, get a full picture, and get a really good user experience. So a couple of goals that we try to do that really kind of provide value to the user. One of those goals is repersonalization. And this really is powered by a lot of data that we capture in the application. So when a user goes into the application, they navigate around, we track what they look at, we track how much time they spend on different articles and different photographs and videos inside there. They can favorite a video, so they have like favorited lists, and we track that information as well. And all that gets stored in DynamoDB. And then we use Lambda function processing in the back to create a profile for this user and a custom feed in Cloud Search. And then that's really what powers personalized content that we pushed over to the user on the application side. And this is also an example of why we kind of have content stored in two places. So earlier on, when we bring content over, we put it into DynamoDB and Cloud Search. When we create a personalized feed, we take the raw content, we put it into DynamoDB, and recreate the indexes and the feeds in Cloud Search there. We did look at Elasticsearch as an option to Cloud Search, and we found that we really didn't need some of the extensions that you would use with Elasticsearch. So for example, we're not doing things that would need ELK or Kibana and kind of stuff on top of it. So the simplicity of using Cloud Search as a managed solution just worked for us. And we have that with auto-scaling of like 2 nodes to get some redundancy out of it. Now another part really we're doing personalization really is the push notifications. So once somebody comes to your app and they take a look and they browse around, they're like, okay, looks kind of cool, I'll come back later. And they really don't get a feel for when to come back. So how do you bring the user back to the application? And we use SNS for this, and we support iOS and Android devices. And we allow you to kind of have as many devices as you want. So the real goal that we wanted to work around was trying to make sure we are thoughtful and respectful of the user's time, right? So when we support multiple devices, we allow the user to pick a preferred device. I got 2 kids. We have like 5 devices between the kids and my phone sitting somewhere. And since this is designed to kind of work with the telecom, a lot of this is maybe being used at home. So if you get a notification, you really don't want 5 devices buzzing at the same time, right? So you can pick a preferred one, and that kind of helps that experience get a little bit better. Also, another part is we try to respect users' like sleep time, right? So we give you quiet hours. So while someone's editing and managing this application in the US, we don't want them to accidentally wake you up at night. So we allow you to have silent hours, quiet hours that kind of improve the experience too. And since a lot of this is based on personalization, and a profile can sometimes recommend 4 things one day, but the next day a couple just fewer things, we try to limit how many push notifications we send you, because the last thing we want to do is kind of become noise, right? You become noise, you get annoyed with the push notification, you turn it off, and then usually you don't turn it back on, right? So what we really found is that using SNS and so on worked out well, and it allowed us to really focus on the features of the application versus just trying to build out the basics of how you kind of just orchestrate and deliver push notifications. So we did hit a couple issues. So as we were building the application, we found that we had a lot of metadata on the text content, but the images didn't really have a lot of metadata. And that would really be something that would inhibit how we surface content that's not tied to an article. Right? So since we're trying to create an experience where you can see images, photo galleries, video, not just magazine articles, we need to make sure we can surface and personalize that. And a big part of National Geographic is the photography as well. So we have given a choice. Either we ask our producers to go back and re-tag images, and that would really be really cost prohibitive and time consuming. And also, because we have so much content, they have to pick and choose what they really want to tag, which really wouldn't allow us to deliver up to our promise. So this is really where recognition really helped out as a plug-and-play mechanism. We pulled it in. It gives us a pretty good confidence level, and it worked out really well on label detection. And it really allowed us to do two things. Not only just surface and kind of apply metadata to the content, but also give us the understanding of what's in the image. So for example, some of our asynchronous processing does some smart cropping, where we try to find a focal point in the image and then crop the image, so we don't need people to go in and crop all the images. In this case, if we find out that an image actually has a map or a chart, we don't crop it. We letterbox it, make it fit the aspect ratio, so you can see the full image. And this way, we kind of had a bit better decision-making on automated cropping. Now, a couple issues we hit with this is that along the way, we had a couple of cases where we were blowing past the 1.5 gigabyte RAM limit in Lambda functions. And it took us quite a little while to find out what the issue was. And it turned out to be a really simple issue. It was like our uncompressed images on the file system were 15 megs. But when you kind of have to you decompress it and you kind of encode it to kind of send it to recognition, it was going over 1.5 gigs. And the real lesson that we learned here was that you really don't need large images to get accuracy recognition. So we kind of go back in and we kind of process and resize the images earlier to kind of fit within that kind of service limit. And also we found that for us at least, the average response time recognition was 1.5 to 2 seconds. And that makes it not appropriate, at least for our expectation on the runtime side, something more you want to use on the background processing. But even then, right, you need to understand really how it's going to work to understand what your workload is. If you have a lot of images coming in, you have cases where you have bulk images coming in, you might do bulk migration, you might get backed up for a while. So you need to kind of understand how you want to handle the throughput, how many images you want to send, how you understand errors and logging and so on. But the real message here is you need to look at the service, understand the service, really play with it, experiment with it to kind of extract the full value of what you want to get. A couple of things that we're going to look at in the future is like really how we handle state in the application. So we have a couple of phases in the pipeline. And right now we have Lambda managing Lambda, which is good, but it adds some complexity to the code. And that's something we'll come back and take a look at in the future as well. Now, any mobile app is not going to be worth a salt if it's not performant, right? Because if you're sitting there and you're clicking for you're waiting for like 5 seconds, you don't get the content, you're pretty much done, you're gone. So what we found is when we use API Gateway, it really didn't add much on overhead. So the chart is on the right. The fact that you can't see a difference between the two lines, that means their overhead is really low. And most of the time, in the duration for API Gateway really was tied to the actual integration Lambda, which is Lambda actually executing code. One thing to note here is that we don't use authorization Lambdas, and most of our authorization is done in code. So that's not really adding some overhead. On the flip side, that does make a couple things easier for us because we just have less Lambdas to manage too. The diagram on the left is really looking at how Lambda reacted to our traffic spikes. And for the most part, we found that that's in blue. It was pretty consistent. Now, one thing to note here is, again, it depends on what your rate of traffic spike growth is, right? For us, the rate of growth wasn't necessarily going from 1,000 to 20,000 a second. It was a smaller growth. So we really didn't have too many challenges here. But as you build this out, you need to kind of understand what your traffic expectations might be and then really fine-tune and optimize. And David did a really good job talking about the container lifecycle, how you optimize. And there's a key message there. With serverless, it's really easy to get started, and that's really part of the beauty of serverless. But at the same time, if you really want to use it well, you need to understand how it really works. You need to understand the service limits. You need to understand why the service limits are there, how it's architected behind the scenes, And once you understand that better, you can really extract more value out of your services and how you kind of use the system. And that's a case where if you understand cold starts versus warm starts, what's the pattern of traffic going to be in the application, it helps you out. So in our case, when we don't use the authorization Lambda and we have one Lambda per API, it simplifies our backup solution for how we're going to keep the Lambdas warm, right? So you really need to take a look at that and really spend some time with it. Just because you can get started early doesn't mean it's going to perform right there on day one. A couple of things also we kind of hit on is the DynamoDB performance was pretty good for us. And part of that was we tried to separate read tables versus write tables as much as possible. In some cases you can't, and you have tables that do both. But if you can, then you can try to optimize your partition logic and your sort keys on DynamoDB tables for that purpose. That helps you get some benefit out of it as well. And that really just goes to illustrate the earlier point on understanding the service a bit deeper. So what's next for us, right? So as I mentioned before, we have Lambda code managing Lambda code, and in some cases that's really good to do, and in some cases it's not. So we want to go back and take a look at some of the features that were launched while we were in development and see if that's going to be useful to us. So step functions is one. If that doesn't work out, we might look at a simple workflow service and see how that fits in. We really have version 1 of our personalization service right now, and it's great when you have nothing and you have something. It really gets you forward. It really allows you to understand how your users interact with our service, so it's really beneficial. But now we want to go back and take a look, how do we take that further? Right, so there are a couple of things we want to go back and kind of really iterate on our side. And another part that really comes up also is metrics. So you get a good, healthy number of metrics with CloudWatch, but there are cases where you're going to need to go in and put custom metrics in, depending on what you want to look at. And we do have some, but we need to go back and add some more. And custom metrics can be tricky, because if you're trying to compensate for some metrics you're used to in the old world that's not available now, and you're trying to design it out, you could have an error in your own metric logic that kind of now gives you a false positive of how things are working. So we need to go back and take a look at how that works and how we kind of enhance that to get some more visibility as well. So in short, really, we really had a good experience, our first experience with serverless. We found that a lot of the scaling issues, really, we didn't have to worry about it. It worked out of the box, as long as we spend the time to understand the system. And all this really allowed us to spend time on feature development, which is really where you want to be, right? So it's great with Amazon that you can pay as you go, and that's really cool. But also, spending time on the right features is really important. I mean, every user expects the mobile apps to get updated every 2 weeks in the App Store. You're going to be doing a lot of development of the apps and improving features. So you want to make sure you're keeping in mind the opportunity cost of not working on the right features. Because your goal is to create a good product experience. What we found was that using serverless tech so far allowed us to really focus on the experience of the application, not on generic orchestration that we don't need to use, and also use some ready-made features that we don't have to build ourselves. So hopefully that was some useful information for you. And if you try it out, as I would recommend you do, come back and share your experience as well. And that's it. Thank you.
Thank you very much. Nick and I will hang outside for a little bit to answer any questions that you might have. So yeah, please feel free to ask any questions. Thank you.
Thanks.